Hello, linear algebra students, Math 2318. This is your first hour of lecture on the math, okay? And we start with section 4.1 because that's when they introduce the concept of a vector space. And it's good for you to have that overriding definition of a vector space at first, so that when you have to broaden your understanding of vector spaces later, you're prepared for that. That's the first reason. The second reason is that if I give you the tools of section 4.1, chapters 1, 2, and 3 are much easier. You'll have more powerful analytic tools to use. So that makes that go in better. All right, so starting with the definition of a vector space, okay? So a vector space, what is that? That is a six-tuple, meaning there are 6 objects required and they have to satisfy all these properties, which are called axioms because the properties are just given. We're not proving them to you, we're giving you these, okay? So all this is part of the definition. So a vector space is a set V, a non-empty set. There's got to be something in there. Elements in there are called vectors. There has to be a binary operation plus, so that if you had 2 vectors, U and V, you could add them. And there has to be an identity for that addition, which we call the zero vector. Every object in V is a vector, including its zero vector. For you and me to talk about things by writing and say, oh, that's a vector, we have to put an arrow over it, okay? To distinguish it from this set, F, which is a field, a certain set of numbers. I'll give you the long story on that. A field is a set of numbers like the set of reals, or the set of complex numbers, or maybe just the set of rational numbers. That has to be closed under addition and closed under multiplication for every non-zero element. Okay, so just think of the reals or complex numbers or the rational numbers at first when you're thinking about what a field is. Okay, back over here. So if you have a non-empty set of vectors and an associated, sometimes we'll say underlying field. I'll hear that phrase. And with that field is another operation called scalar multiplication. You're going to see how that works in a minute. But the things that are in the field often get called scalars. So you start with a set of vectors, an associated field of scalars. There's this strange multiplication that glues those things together. And we're going to call all that a vector space if we have these 10 properties are satisfied. So in the next video, I'm going to be going through the same list, but right next to it, giving you an example of a vector space, which is actually a set of functions, the set of all functions defined on the reals. And I'm going to be showing you how proving that that is a vector space, we have to go through and satisfy all those properties, okay? Now to be able to get through this, all this discussion a little more quickly in terms of the notation, I use a lot of shortcut notation. So for example, down here, can you see that? Let's see. Yeah, down here, I'm saying all these 10 properties have to hold if for all U, V, and W. That means I'm just listing out a bunch of things I might be calling what? Vectors, because they are elements in, that's what that epsilon stands for, V, this thing that's my set of vectors. And for all, that notation is a way of saying more quickly these 2 words. And for all C and D in scalars in the field, ... we have all these properties hold. Just to give you the heads up, that kind of notation is going to be used a lot in this class. So I just wanted to make sure that you had a resource for all those in a oneer. So for example, that again is the universal quantifier. It's read as for all or for every. This one is called the existential quantifier. That means there is at least one or there are some. You can read it differently in English depending on the context. And this little epsilon is sometimes read as the word is or is an element of. So if I write little a, epsilon, big A, that's read as little a is an element of the set A. And I'll use ST for shorthand for such that. All right, so back to describing all these properties, all these axioms that have to be satisfied if we to define what a vector space is. So axiom 1 says for all u and v vectors in the vector space, it has to be true that their sum under this type of addition that was given over here, right here, their sum is in V. Okay. So we describe that axiom as V is closed under vector addition. Okay, that's the way that property is described. You'll be seeing that, reference that, and you'll want to use those kinds of terminology as well. Axiom 2, if u plus v is a vector in the vector space, that's the same thing you would get if you added v plus u in that order. So we say that vector addition is a commutative. Commutative, I tell my students, think of the word commuter. That means the v and the u can move around and it's still the same thing. They can commute, right? Axiom 3. If you first add u to v and then add the vector w, you should be getting the same thing as if you had first added v plus w and then added u. So we say that the vector addition is associative. Vector addition is associative. Axiom 4. There has to be a vector in the vector space V that acts like the additive identity for vector addition. So additive identity 0 with a vector symbol over it. The 0 vector has to be in the vector space. There has to be one, something that acts like that. Okay, and this is true for any vector in there. It has to be true that for any vector in the vector space V, if you add the 0 vector to it, you're going to just get that vector back. Okay, so we had an additive identity exists. Axiom 5. For all vectors in the vector space, for each one of them, there has to exist another vector, W, for which it's true that V plus W is equal to the 0 vector. Okay. All right, so what we say here is that we have the existence of additive inverses. Okay. Axiom 6. For all vectors in the vector space, for all scalars that are out in that field, it has to be true that C times V, this is this, we're defining this scalar multiplication now, or we're giving a property of it, defining it by giving a property of it, or at the same time, any scalar from the field with that particular scalar multiplication times a vector, right? So we're taking a scalar, which is in a different set, and the vector, which is in a different set, and somehow combining them, and we're saying, well, whatever it is, the result has to be in the vector space. It has to be a vector. Axiom 7, that scalar multiplication is distributive. A scalar times a sum of vectors is the same thing as that same scalar times that same scalar times that vector, and then you add those vectors. which you can do, right? Because you've already assumed that anytime you have C times a vector, that's a vector in the vector space. So that vector addition makes sense there. Axiom 8, the associativity works in the opposite direction. If you take two scalars in your field, like two real numbers, and add them, and take that sum and use it as a scalar on this vector u, you'll get the same result as if you had taken the first one with that vector, scaled it up first, the second scalar with that same vector, got that as to be a vector, and then added those two vectors. Same thing should result. It should be true that if you have, so this is kind of like associativity of scalar multiplication. You scale up a vector u, and then you scale it up with c, first with d and then with c. Well, it's the same thing as if you had multiplied those two scalars, like two real numbers or two complex numbers, and their product and multiplied it by, or scalar multiplied it by that vector. You should get the same result. And finally, this one needs a little work. This one, which is from the field, right? That was that sixth element of the sextuple. There has to be an identity for the scalar multiplication. Something that that scalar times any vector just gives you back that scalar. So if you have all these properties, you have the vector space. Okay, so the next video, I'm going to go through this using this checklist and show you an example of a vector space. Not maybe the first one you might think of.